Hello everyone, my name is Yao Wei and I'm from King's College London. Today I would like to share my research about the rational design of the molybdenum clusters and about the relevant catalysis and absorption with the particle swarm optimization. So first of all, we know that molybdenum material is very important in the physics and chemistry, and it plays a very important role to do the catalysis. So what we did in this research, we designed a very whole process from the cluster search to the final chemistry reaction. So please listen to me what we have. So first of all, let's say that what we did for the cluster. So you can see that there are 5 atoms clusters we put here, and we used some structure search material software like ELSE, and we can see even though some of the clusters are very similar, just like from 3,1 to 3,3, the bond length is a very huge, very small difference. But why I put them together here? Because the spin multiplicities for them are different. And if we see that the spin density for them, there are huge difference. And also, what we did is that we calculate the free energy by the vibration for them. So just like, for example, for the 3 atoms cluster, you can see that 3,3 has the highest energy at the beginning, but with the temperature increase, the energy goes down very quickly, and above the 150 Kelvin, the energy is the lowest one. So I want to see that when we search or find some unknown cluster, we must not only use the DFT to choose the different multiplicity, but also we need to concern about the temperature because it's very important for the stable. And after that, I want to show what is important in this calculation. So you can see that we use the 2 different potentials here. One is the hard potential with the 14 electrons. Another one is the 6 electrons with the soft one. But we can see the results has a big gap. So for the hard potential, the results are close to the experiments. But for the soft potential, they are the bond length for the dimer mole, there are around 0.2 angstrom. So in this research, we choose the hard potential for whole calculation. And also, if we use structure search material software, we should get a lot of structures. So as it's shown, like here, we searched from 3 atoms cluster to 10 atoms cluster, and because there are so many, so we choose the relative energy lower one, just the blue one. So here I want to show next, when we get the cluster, what we can do next. So when we get the cluster, we need to absorb on the surface. Yeah. So we choose a long repeating surface units, and after that, we absorb a molecule near the cluster. So how can we find the best place to absorb the cluster? This is a very good question, because it will influence our catalysis. So let me tell you one by one. So first of all, if we have a cluster and want to absorb on the surface, we must to make this cluster charged. So here we take the 6 atoms cluster, for example, and the 6th one is the lowest charged cluster. And also, because it has been charged, so the symmetry has been break. So the symmetry is just the C1. And when I get the charged cluster, what I do next? I just want to put it on the surface, on the graphene surface, but I want to control the 5D multi-objective for it. So it's 3 degrees and 2 translations on this surface. So I want to rotate it and translate it. And for that, we need to plot the potential energy surface like it, and then we can know where is the best places to absorb. So here we try to use the 2 multiplicity 1 and 3, and we can see on the left hand side we have the minimum. We use the PSO to search the 5D multi-objective, and we can see the minimum is very small. So that means, and the potential energy surface is very complex. So that means if we don't use this way, we should get the wrong results. We cannot just do the catalysis analysis just by putting a cluster on the surface and relax it. Then we must be wrong. So we should use a science method to search to find where is the minimum point on the whole potential energy surface. Okay, so by this method, I found that 611 is the best place for the cluster to absorb on the surface, and I want to show you that there are so many structures we found. There are just like 25 structures we found all within 1.8 electronvolts. So if we don't do like this, we are very easy to get a wrong result. And after that, we use the same method to absorb the CO molecule near the cluster, and also we get more than 20 structures over a total spread of the 2.67 electron volts. Okay, so here we find which one is the best structure for the CO molecule absorbed on the cluster on the surface. So what we can do next? So what I can do next is that I want to break the C and O. So here we get 2 different situations. One is this one, we break the carbon and oxide bond, and the other one is this one. And here we calculate the boundary for it. And also I want to show you that if we define this status is the N0, and this one is N1, and this one is N2, what I can do next is that I can calculate the chemical reaction. So like this one, I calculate 2 situations. One is 400 Kelvin, another one is 500 Kelvin. And at the beginning, the N0 is the population is 1, and if we consider 400 Kelvin, maybe the reaction will happens in 4.5 times 10 to power 7 second. But if we increase the temperature to 500 Kelvin, the reaction will happen in 4.5 times 10 to power 3 second. So the time decreased a lot. So that means in our calculation, the temperature increase, the reaction will be more and more quickly. Okay, so this is the whole process from the beginning of the structure search to the final chemical reaction. So I want to conclude what we did. So first of all, the most stable cluster we found, and we absorb it on the surface, and also absorb the molecule on the cluster. And the second thing is that we consider all possibilities for the chemical reaction of the interested catalysis. And the third one is we simulate the populations of the reactants and the products of the reactions. So last, I would like to thank my supervisor and my colleague. And also, I would like to thank some institute to provide funding and the HPC for me. And if you have some interest about my research, you can refer this to papers or send email to me.